Hi everyone, and welcome to the second of 4 videos looking at some past paper questions on the topic of strong bases and kW. This question here is a little bit of an unusual one. We've got to do something with a graph here, but we'll come to that in a second. First thing, it says write the expression for kW, so that's nice and easy. kW is the H plus concentration times the OH minus concentration. It's the ionic product of water, isn't it? So it's multiplying the concentrations of the two ions from water. Right, it then says, calculate the OH minus concentration in a solution of hydrochloric acid with a pH of 4.37 at 25 degrees. Okay, so this is going back to similar sort of question as in the previous video, where we're actually calculating the OH minus concentration in a solution of an acid. Okay, so we are expecting the OH minus concentration to be very, very low. Okay, so if we use that kW expression that we've just written, and it's asking us to calculate the OH minus concentration, so we need to rearrange this. OH minus concentration is going to be kW divided by the H plus concentration. So therefore it's going to be kW has the value of 1 times 10 to the minus 14. And the H plus concentration, or if the pH is 4.37, the H plus concentration is going to be 10 to the minus 4.37. So therefore, we just need to work that out. 10 to the minus 14 divided by 10 to the minus 4.37. 2.34 times 10 to the minus 10. So again, it is a very, very low concentration, which is what we were expecting. Right, we haven't actually had to do anything with this graph yet. This question carries on over the page. Let's have a look at what we're doing here. Using figure 6.1, here we go. Explain whether the dissociation of water is an exothermic or an endothermic process. Okay. Well, dissociation of water, if we go back here, here's our equation for dissociation of water. If water's dissociating, you're breaking the bond, aren't you? Okay, so you are breaking a bond, so it's going to be an endothermic process. Every time you break a bond, you have to put energy in, so it's endothermic. But the question says, using figure 6.1. If we just write down what we've just said, we haven't used figure 6.1 at all, have we? So we need to refer to the graph. Okay, what the graph is showing us is that as the temperature increases, kW increases. Okay, so let's write that, because then we're talking about figure 6.1, aren't we? So figure 6.1 shows that as the temperature increases, the value of kW increases. Well, if we go back to our equilibrium, if you have an equilibrium, then if the temperature increases, then the equilibrium is going to shift to decrease the temperature, which shift in the endothermic direction. Okay. Increasing the temperature shifts the equilibrium in the endothermic direction. Okay, because then it counteracts the change and decreases the temperature again. So if kW is increasing, it means the equilibrium is shifted more to the right. Yeah, if kW is getting bigger, it means, given that kW is the concentration of the two ions multiplied together, if that value is getting bigger, it means we must have more of the two ions. So the equilibrium is shifted to the right. So therefore, that it must be the endothermic direction. Okay. So I don't think we need to write anything else there. As the temperature increases, kW is increasing. Increased temperature shifts the equilibrium in the endothermic direction. Therefore, dissociation of water is endothermic. Just make sure we've actually answered that question really clearly. Right, determine the pH of pure water at body temperature. Okay, right. So the difference here is we're at a different temperature. Okay, this whole question has been about kW, so we're going to start with kW. Okay, same as we've talked about in terms of, acids questions, just start by writing out Ka. If it's a question about a base, or, this question is clearly about kW, right? The whole question has been about kW so far. So just start by writing out kW. It's asking us to determine the pH, so therefore we want the H plus concentration. So we're going to have to rearrange it to get the H plus concentration. So it's going to be kW divided by the OH minus concentration. Okay, but so kW, we can get the value of kW. How do we get the OH minus concentration? We can't, we're kind of stuck. So that means we need to go back and have a look at this. What are we doing? We're working out the pH of pure water. What do we know about pure water? Pure water is neutral, isn't it? What does neutral actually mean? Neutral means that the H plus concentration is equal to the OH minus concentration. So therefore, we can say that Kw, instead of being H plus and OH minus, is going to be equal to H plus squared. So therefore, if we want to work out the H plus concentration, it's just going to be the square root of Kw. So actually, we're not doing this. We're going to be doing this instead. Right. If the H plus concentration is the square root of Kw, then what is the value of Kw? Oh, it's 1 times 10 to the minus 14. No, it's not. It's 1 times 10 to the minus 14 at 25 degrees. Okay, remember that Kw is an equilibrium constant, so it will be affected by the temperature. Okay, we're doing it at 37 degrees. Okay, and this is where the graph comes in. Okay, what we now need to do is find 37 degrees on our graph, right? So if that's going to be 35 there, isn't it? So 37 degrees is going to be about here somewhere. Okay, we can't be super accurate here because we've only got a certain number of grid lines, but I reckon that's slightly less than half, isn't it? If we go across from here, you could do this with a ruler, but I don't think that's 2.5. I think that's 2.4. Okay, they're going to give you a range. You don't need to be 100% accurate, but try to be as accurate as you possibly can. So I'm going to go with 2.4 times 10 to the minus 14 as my value. Okay. So we then want to do the square root of that. .55 times 10 to the minus 7. So therefore the pH is the negative log of 1.55 times 10 to the minus 7. And we're going to get 6.81. Does it say 2 decimal places? No, but usually the pH is 2 decimal places. Okay. So that makes sense. It's pure water, so we would expect it to be pH 7, but that's only going to be at 25 degrees. So at a different temperature, the pH is going to be different, but it's not massively different. That does seem like a reasonable answer. Yeah. If we got pH of 2 or something, we've probably done it a bit wrong. Okay. Right, finally, the last question here. We've got a solution of sodium hydroxide. Right, if it's sodium hydroxide, it's a base, so we want to be using Kw. Okay, just get this written out. Calculate the concentration of the sodium hydroxide. So the sodium hydroxide is going to be the OH minus. Okay, remember, because it's a strong base, that's going to completely dissociate. So the concentration of the sodium hydroxide is going to be the same as the concentration of OH minus. So we want to rearrange Kw for the OH minus concentration. We're at 25 degrees in this question, so we can go back to our normal value of Kw. Okay, that's why they always write the temperature. If you notice that we've got the temperature. If we go back to the previous question on the other page, they told us the temperature. You don't really have to do anything with that, but if it says 25 degrees, that's a clue going, you can use the 1 times 10 to the minus 14. If it's anything other than 25 degrees, we can't use that. We had to work out our Kw value off the graph, didn't we? So that 25 degrees is a signal that we can use 1 times 10 to the minus 14. The H plus concentration will be 10 to the minus pH. So we 10 to the minus 13.46. 10 to the minus 14 divided by 10 to the minus 13.46. There we go. 0. Significant figures, no, it doesn't say. So we'll call that 0.29. There we go. So if anything, I think KW is actually simpler than KA in most cases. There's fewer steps involved.